In this work, we are proud to present Learning to Drive is a Free Gift, large-scale, label-free autonomy pre-training from Unposed in the Wild videos. Autonomous driving holds great promise for the future of transportation and driving. You can have near superhuman performance. However, the search for a foundational autonomous driving model with a common sense understanding baked in how to drive is missing. And this begs the question, how can you retrain this model with large internet scale data at the scale of such large NLP and computer vision models? There are a lot of large datasets that exist with a plethora of supervised data, including Waymo Open, Kitty 360, the new NVIDIA physical AI dataset, as well as simulators. However, at the end of the day, none of these are truly internet scale. However, if we look at YouTube egocentric driving data, we find that it is internet scale and provides a massive amount of visual information of how to drive in all kinds of diverse environments. As such, can we learn how to drive from one end-to-end model from only YouTube driving videos? And can such a learned encoder prove useful for challenging driving tasks and downstream tasks? Let's use a 4D-aware model on unposed images and make it into a driving model. Prior work in 3D representations shows that we can have a model such as VGGT that can have a spatial understanding from just images, which are massively available and do not require an explicit 3D structure. Within this class of VGGT models is Pi3, which is simpler than VGGT and trained significantly on dynamic scenes, making it attractive for autonomous driving models. So let us predict both semantics, confidence, point maps, motion, and camera poses, and predict the current results and what we will think will happen in the future for driving, and do this without any labels. We present LFG, a foundational autonomous driving model predicting future and current point maps, camera poses, confidence, semantic, and motion masks from unposed video. Pi3 gives scene tokens after its encoder, which encode the late of where we are, geometry, and confidence. We propose to add a simple autoregressive transformer to causally predict future tokens, which are what we think the scene will evolve to. First, let the Pi3 teacher see all of the frames in the segment of a random video. Then the student, LFG, receives just the current frames as input. LFG's objective is to predict both current and future outputs, only conditioned on the current frames. From current and future scene tokens, LFG predicts both confidence maps, depth maps, and camera poses. To learn segmentation, we employ state-of-the-art model, SegFormer, which is a semantic segmentation model that gives pseudo-ground truth outputs. SegFormer receives both current and future frames, predicting all of them. LFG, on the other hand, must predict the current and future semantics, conditioned only on the current RGB images. To have LFG learn motion, we employ a unique combination of grounded SAM2 and CoTracker3 to learn current and future motion. We first query grounded SAM2, which gives us mask instances over time of pedestrians and vehicles. Then, with each pedestrian and vehicle, we track its 3D position over time with CoTracker3 and the Pi3 teacher output to see if it is truly dynamic. With these pseudo-ground truth outputs, we can predict the motion of n-1 total frames in feed-forward fashion, conditioned only on current RGB images. To train LFG, we use 32 A100 GPUs for 40,000 steps on the OpenDV driving dataset. We train over a few days in multiple stages. First, learning future geometries and ego motion, then segmentation, and finally, the most challenging, motion. We perform experiments on segmentation, point maps, camera pose downstream tasks, as well as the encoder on NavSim v1. On the Kitty 360 dataset, LFG beats its SegFormer teacher on both overall and predicted for future frames. NavSim V1 challenging task. We consider if the encoder is useful enough. We fine-tune the encoder with 3 passed frames at 2 Hz, and for fairness, have causal attention for the other models except LFG, which already has it trained. LFG strongly outperforms its based on different amounts of fine-tuning data. Even against diffusion drive, the existing state-of-the-art on NavSim, LFG beats it in sample efficiency at 1% and 10% NavSim fine-tuning data. Future work will focus on improving the crispness of lens prediction, multiple cameras, and vision transformer distillation within a causal attention head. Thank you for listening, and thank you for the collaborators for helping us.